All right, just a quick recap to this point. So what do we know up to this point? We know linear combinations. Going way back. We know vector independence and dependence, or we should be comfortable with that by now. So vector independence and dependence. We should be comfortable working with matrices. We're working our way through it. 2D lines. You should be able to do the vector form, parametric form, symmetric form, and standard form. So all of these operations you should be comfortable with up to this point. That's everything we've kind of talked about in Unit 2. 3D lines. With 3D lines, you should be able to work with vector form, parametric form, and symmetric form. And you'll notice that we never ever talked about standard form for a 3D line. That explanation is going to come in the next video as to why I haven't talked about that. And then you should be able to find the intersection of two lines in 3 space, because I'm not going to give you a 2 space question on a test. It's just, can you do grade 10 math? I'm not going to waste your time with that. So there's a quick rundown of what we know to this point in time. We're actually going to move on then to our next topic, and now we're looking at the vector equation of a plane. So up to this point I've been just talking about lines. I've made references to planes, and planes you can think of them as a piece of paper, just infinitely long. So you can't see the edges of them unless I draw them, and then you can see the edges. So we're looking at vector equation of a plane. So today I'm able to take given information and create a vector equation of a plane. So that's all I'm looking for today. Straight knowledge and understanding stuff. So in order to determine the equation of a plane, so again, a plane is a piece of paper, infinitely long. So I'm going to draw the infinitely long and wide piece of paper on the board here. So there is my plane. So in order to have enough information about it, what will I need? All right. So I know I see hands up everywhere. Unfortunately, I can't call on you, so I'm going to help you out. You still need a point. Okay, we need a reference point on the plane. So somewhere on the plane, we need to know a point, P naught. Now with a line, we needed to know a direction vector. So on this plane, we needed to, or if it was a line, so going through P naught, so let's say it was going this direction, we needed to have a direction vector. But now our line has width, so to speak. So rather than being infinitely thin, we now have some width. So we need a vector that will take us off this plane, or this line, and veer off in another direction. Okay? So what we do in order to veer off in another direction is we provide ourselves with a second direction vector. So now a point, and what we need is 2 direction vectors instead of 1. And that is the only difference between the two. So moving along then, the equation and equations of plane and notation here. So we talked about our vector form. So vector form x, y, z equals our point a, b, c plus our first direction vector. So d1, d2, d3, and now we have a second direction vector. Let's pick an M here, and I'll go with d4, d5, d6. All right, so there's our vector form. Can we write it as parametric? You bet. Now the difference is, you'll remember that I use this notation for line. For a plane, we use the Greek letter pi. So there is your notation for a plane. And it's going to look like this. The constant A plus TD1 plus MD4 with using our notation here. B plus TD2 plus MD5. Z equals C plus D3 TD3 plus MD6. So the only new, or the only thing that looks different today from our line, is this third column, or sorry, well, technically third column here, but it's the second direction vector. So there's an additional term or set of terms in our equation. What about symmetric form? Do you remember how we got symmetric form before? Symmetric form was when we were letting each of the variables equal our t value. So what we were doing is, this is what we had in parametric form. So we set everything equal to t because every equation had a t in it. Now there's multiple scalar values. There's m's and t's now. So what happens is that we need to ask ourselves, is it possible to solve these equations for t and m? And the answer is no. And because we can't isolate t and m at the same time, no symmetric form exists. All right, so there is no symmetric form for a plane. So on a test, when I ask for the symmetric form of a plane, it is not a trick question. It is a question as to whether you understand the requirements for a symmetric form of an equation. So you can put a star on that. Definitely going to put a question like that on the test. So please be aware. Moving along then, determine the vector and parametric equation of a plane passing through those 3 points. And again, I can't stress this enough. These are points when we have rounded brackets and there's a capital letter accompanying them. Okay, so very careful on the test. So what are the requirements in order to solve for the equation? First we need a point. We have lots of points. We have 3, so that's done. And we need 2 direction vectors. So 2 direction vectors. So how do we find those? Well, if you have 3 points, then you have lots of information for direction vector. So our first direction vector will be vector AB. And jumping straight to final answer then, the vector would be a 3, -7, -3. If you do not understand where that came from, then you do not understand how to find direction vectors well enough, and that's something you need to come see me about, because that is how quick it should be moving along. So vector AC then should be a 0, -5, and a 1. So there are my 2 direction vectors. So now I have lots of information. I can now find my vector equation of a plane. So x, y, z equals, I'll just pick point A as my reference point, plus 3, -7, -3, plus m, 0, -5, and 1. It also wants parametric. So x equals 1 plus 3t. The m value is a 0, so don't have to write that in. 7 minus 7t minus 5m. And z equals 2 minus 3t plus m. So there's your final answer, those 2 formats right there. Any questions? Obviously not, because I can't hear you anyway. Okay, determine 2 direction vectors for each of the planes listed below. So a plane parallels. You need to watch your keywords here. Parallel. So if it's parallel, that means that it has to be, the plane has to be oriented, or the piece of paper has to be oriented in the same way as the other piece of paper. So the only way to ensure that is that they share the same direction vectors. So I could pick a new reference point that's not on the given plane and use the same direction vectors, and I would end up with direction vectors that would provide me with a parallel plane. Next one, the plane passing through that point P, 210, and contains that line X, Y, Z in symmetric form. So, plane passing through that point and contains this line. So that means that in a diagram here, that line is on the plane. So we need the direction vector from the line. So the first direction vector coming from that line is going to be the denominators. 1, -2, and 3. That's because the direction vector denominators are always in an symmetric form. How do we find that second coordinate, or the second direction vector? We know it passes through point P, but we need another piece of information. For people that said, let's use the reference point from the line that we know is on the plane, you're absolutely correct. So using the point from the line, and I'll call that point A, which would be a 0, 1, 1. We can then find the second direction vector by finding the vector AP. We know P is on our new plane. We also know point A is on our plane because that line is on our new plane. So finding point AP, we would have 2, 0, -1, and there's my second direction vector. Okay, that line, the green line there, it was on the plane. It's going to be part of our new plane, so any point in that plane is actually something I could use, so I don't have to use the reference point. It's just the easiest. Now the XZ plane. So two direction vectors in the XZ plane. You just want to make sure that they have an X component, so 1, 0, 0. So that would point down the x-axis. And keeping it simple, here's a vector that points down the z-axis. So that we have perpendicular vectors. Not that that's important, but they are perpendicular. They point down each axis, and that provides us with two different directions, which allows us to create that plane.